Hello, my name is Andreas Quist. This is my video sample for admission to graduate studies at the University of Washington Math Department. Today we will be talking about homogeneous linear differential equations in the second order with constant coefficients. So this is a differential equation of the form a d squared y dt squared plus b dy dt plus cy equals 0. Where a is not equal to 0, and we will also assume for simplicity that b squared is not equal to 4ac, which might clue you into what we're going to do. So we know that this equation, being second order and linear, has exactly two distinct linearly independent solutions. So if we guess and figure out two solutions to this equation, then we've found the general solution. We're going to start by making an educated guess about what that solution looks like. So we're going to say y of t. We're going to guess that y of t is an exponential e to the rt for some r in c. This has the nice property that, of course, d to the ny dtn is equal to r to the ny. So plugging this into our differential equation, we get an equation of the form a r squared y plus b r y plus cy equals 0. Of course, being an exponential, y is non-zero for any complex r and real t. So we can divide by y out of this equation and get a quadratic in r, a r squared plus br plus c equals 0. If we solve this equation using the quadratic formula, we get two unique solutions since the discriminant is non-zero, and we will write those as r1 and r2. So we've found two solutions that work. Y1 of t is equal to e to the r1t. Y2 of t equal to e to the r2t. And of course, when we plug these in, we will get this equation. Dividing out by y, we get this, and since r1 is a solution to this, we know that we actually get 0. So this is in fact a solution to our differential equation. Now we want to know that these two are linearly independent, and if they are, then we're done because we found two independent solutions to the equation. To do that, we compute the Wronskian, which is w of y1, y2 is the determinant of matrix M, where Mij is the I minus 1th derivative of the jth solution. So we want to know that the Wronskian is never 0 on our domain, which is the real numbers for t in the real numbers. So we write w of y1, y2 of t is equal to the determinant y1, r1, y1, which is the derivative of y1, y2, r2, y2, the derivative of y2. This gives us r2, y1, y2 minus r1, y1, y2, which is, when we plug things in, y1 times y2 is going to be the product of the exponentials, so it's going to be the e to the r1 plus r2t. So we get r2 minus r1 times e to the r1 plus r2t. This, again, is an exponential with a complex scale and a real number. So this exponential right here is non-zero. So this Wronskian is 0 if and only if r2 minus r1 is 0, but then r2 would equal r1, and we showed here assuming that the discriminant was non-zero, we know by assumption that R2 and R1 are distinct. So that means that y2 and y1 are linearly independent. So we found two linearly independent solutions to this equation, which means we can write the general solution y of t equals c1 e to the r1t plus c2 e to the r2t for c1, c2 in the complex numbers, and there's our solution to the differential equation. Thank you.